Hello, everybody. I'm Rituraj, and today I will talk about the effectiveness of rule-based systems as opposed to machine learning in the context of today's autonomous driving. And I will also go into autonomous driving into more detail as well. So let me give you a self-introduction real quick. I'm currently a student at the University of Washington at Seattle, and I'm pursuing a bachelor's degree in computer science. I'm going into my sophomore year this fall. I'm also now a software engineer learning web development here at Code Chrysalis. And in terms of engineering, I don't know exactly what I'm interested in, but I really like development, making new things, as well as machine learning and automation. Furthermore, I also love cars, and therefore the presentation topic is born, autonomous driving. So why autonomous driving? Why do we need autonomous cars? This can be broken down into three main factors: cleanliness, comfort, and safety. When I talk about cleanliness, I talk about reduced energy consumption. Autonomous cars are far more efficient and use far less energy than a human driver would. And that's a very positive thing for the planet. Next, we get into comfort. The key factor of comfort is mobility. Especially for people who are older and cannot drive, mobility is a key, and autonomous driving provides mobility to these sorts of people. Furthermore, we talk about the efficient use of time. I read this statistic recently where we spend about 7/10 of a year just searching for parking. If you imagine all the time you spend driving and the commute time, we could use that time to do something else, something maybe more productive, because the autonomous car will handle the driving portion for you. And the most important factor why we need autonomous driving is safety. There's over 1.25 million deaths in road accidents every year, and 90% of them are due to human error. And autonomous driving looks to solve this problem. So now I'll talk about the concept of autonomous driving by first introducing a few key terms. AD is referred to as autonomous driving, and ADAS is advanced driving assistive systems. What these mean exactly, I will go over in the slides to come. So here is the Society of Automotive Engineers standardized quantification of the levels of automation. So we start from level 0 to level 5. Level 0 is just a placeholder. It's basically zero automation, 100% control by the driver. Levels 1 and 2 is where we talk about ADAS. It's where we have some assistance from the car, but the driver is still very, very necessary. To give an example of this, let's take a feature such as lane assist. Let's say you're cruising down the highway and you want to center the car in the middle of the lane you're driving. That feature can be taken care of by the car. It's implemented in many vehicles today. That could be referred to as partial automation. The driver is still a necessity, but some features are handled by the car. Level 3 onwards is where we get a little more autonomous. The driver becomes less and less necessary, and by level 5, we don't need the driver at all. So let me talk about the history of automation from when it began back in 2005 to where it is today. Mainly, we have been dealing or dabbling with, to the best of my knowledge, the field of ADAS. We have reached levels 1 and 2 and are developing levels 3 and 4. And the furthest I believe a company has got to a deployed version is a level 4 car. But with ADAS itself, we have managed to save millions of lives. So the future, the potential for autonomous driving is indeed quite bright. So now that I've talked about the history of autonomous driving and some key concepts, I would like to go into how exactly autonomous cars work. How autonomous cars work can be broken down into 6 distinct steps. The first of which is HD maps. This is the thing you can see on the right here. This is an example of an HD map. It's essentially a 3D representation of the road network. Next is localization. This is the car pinpointing its exact location on the HD map. Next is perception, computer vision. It's as it sounds. It's the car's version of visualizing the environments around it. That involves classification, like classifying whether something is a person, a car, a truck, a traffic light, and whatnot. Next, we go into prediction. This is the car predicting the behavior of the objects around it. whether it be pedestrians, cyclists, other cars. After doing this prediction, the car can move on to plan its own trajectory on where it needs to go. This is known as planning. And finally, after we have planned where exactly we need to go, we can execute the very last step, which is control. Control is the car actually accelerating, steering, and braking in order to get from its current location to its target. So now that I've given you a brief overview, let me go into each of these concepts in detail. What is an HD map, you ask? This is an HD map on the bottom left-hand side of the screen. It's essentially an accurate 3D representation of the entire road network. But if you notice a little closely, it's not just that. It contains a lot of semantic information in order to aid the car do the steps to come. Essentially, it has things such as the exact height of the traffic lights, or the exact height of how tall the traffic lights are, where the walls are, how wide is the lane, where the poles are, where the barriers are. All this information is crucial for the car in order to take the next steps. Furthermore, we have the precision, which is unparalleled. If you look at the navigation maps on your phone or on your car's infotainment system, for example, they offer meter level precision. If I were to give an example of that working in real life, it wouldn't go too well. If you look at the image on the bottom right, let's say you want to parallel park your car, but there's water to the right of you and there's the road to the left. With meter level precision, you either fall into the water or you park a little to the left and you get cars rammed into you, which isn't ideal. Therefore, we need centimeter level precision for autonomous cars to function safely and properly. Now that we have HD maps, we come into localization, which is the car knowing its exact location on the Earth. This is done through something called, one of the approaches it is done through is called GNSS RTK, which stands for Global Navigation Satellite System and Real-Time Kinematics, big words. But what it basically is gaining information from a minimum of 3 satellites, which communicate to satellite stations on the ground. Now I've given you a lot of textual idea of how this works. Let me actually visualize it for you. Let's say you're on a field and you're lost and you want to find out exactly where you are. I tell you that there's a tree 75 meters away from you. At this point, you still have no clue where you are. You could be anywhere on the diameter or on the circumference of the circle. Next, I tell you that there's a house 64 meters from where you are. Now you have a clearer idea of where you can be. You can be on either intersection of these circles, but still you're not 100% sure. Now I tell you that there is a light pole 55 meters from where you're standing. At this point, it becomes clear. You are on the intersection of these 3 circles. So essentially, instead of having houses and light poles and trees, we have satellites, which communicate to satellite stations on the ground, which basically broadcasts the car's location. And essentially what RTK is the real-time application of this. The car, as we know, is not going to be static. We have to go places. So as the car is moving, this process is happening constantly. But it does have its drawbacks, which is the fact that these satellites don't work too well when there's obstructions such as extremely tall buildings or rough weather conditions. We need a complementary approach to localization, which happens through something called sensor fusion. So our car has a lot of sensors, such as cameras, radars, lidars. Cameras, obviously, like the camera on your phone, gets the clear image. Radars are worked through radio waves, and lidars work through lasers. So we need the data from all these to accurately keep mapping ourselves on the HD map and not lose control of where we are. And these 3 sensors, when we combine the data from them, we call it sensor fusion. A very useful thing in the whole process about autonomous driving, even in the next step. Next step, perception, computer vision. This is where the core AI comes in. We classify objects around our car and we make labels for them. Okay, that's a pedestrian, that's a car, that's a bus. So we use a lot of artificial intelligence here, and we use different learning ideas to train these models. I'll be going to supervised learning for this presentation. And once again, in order to test our model, we need these 3 sensors and we need the data fused from them because that's what the car is actually visualizing in real time. So the way the learning works is essentially we're passing in millions of images and we're assigning a ground truth value to them, which is basically saying, okay, here's a picture this is a car. The computer is going to know that. We're passing that value in. So essentially how this works is that we feed our image forward into these red circles. And the blue layers are actually feature vectors that the model extracts itself. We can only specify the number of layers, but the features are something that the model extracts. And to visualize features, you can think of something like, we have a car. The way we know it's a car is maybe it has wheels and it has windows. That could be layer 1, layer 2. Of course, in real life, there's many, many more layers. And artificial neurons don't think the way we do. So the layers are probably not about windows and wheels. It's much more complex than that. But essentially, we get an output from the car. And as you can see, the output in this model is quite far away from what our ground truth value is. We have an error, quite a significant error. So what we do with this error is we send it back, all the way back to our model. It goes through this layer, back to the inputs. And what it does as it goes back is it modifies the feature vectors slightly. So when it feeds forward again, we have an error that is smaller. This is known as back propagation. And essentially after millions and millions of these cycles, because it doesn't happen instantly, we get an error that is as small as possible, and the output is as close to the ground truth as possible. So when we actually test it with our camera and radars and lidars in the real world, and we see things around, we can say, oh, this is a pedestrian, this is a vehicle, through all this training. That's how the core training perception actually works. Next, we have prediction. This is the car predicting the behavior of other vehicles, other people, other objects in general around it. This is done through both data-driven and model-based prediction, as I will go into in the next image. So here's how we can visualize our data-driven prediction. Let's say we are the blue car, and our objective is to make a right turn. But in order to do that, we have to know the movements of the white car, because it could pose a safety hazard if the car doesn't take a right turn and actually goes right through. We could crash into it. So what we do essentially to train our model, which currently doesn't have any idea, is we pass millions of scenarios to our model. The same situation, but the white car doing different things. In one, it might go straight. In one, it might actually take a right. And from these scenarios, our blue car learns the behavior of the white car. So when the white car makes the slightest move in the real world, our model can tell exactly where it's going to go. For example, if the white car actually doesn't decide to go right and actually crosses the zebra crossing, we know that the car is going straight. We need to stop. If it makes a right turn, if it puts on the indicator, for example, then we know the car is going to make a right turn. We can proceed safely. And this planning of where to go takes place in the next phase, which is planning. Now, the key point of planning is actually something called routing, because planning is an extremely mathematical process, and dealing with mathematics in HD maps is extremely difficult. So what we do is essentially the car converts the HD map into a data structure that we actually covered here in the bootcamp. It converts it into a graph, because that is far easier to deal with mathematically when you have nodes and edges instead of having a full network of HD maps with all the semantic information. So essentially, planning comes down to something called lattice planning, and that is extracting ST and LS graphs. Essentially what this is we're analyzing data in 3 dimensions: latitude, longitude, and time. So the ST stands for the longitude versus time, and LS stands for latitude versus longitude. So this arrow over here is the longitude time, and this horizontal line here is the latitude, longitude. And essentially, we use the data we got from prediction. We know where the other objects are going to move. We can plan our own trajectory by using these 2 graphs. This is essentially the car mapping out where it needs to go. It's a highly mathematical process, and in the interest of time, I will not go deeper into the mathematics, but these are the 2 main concepts: routing and lattice planning. Next, we go into control. Voila, we have done everything. We know exactly where we need to go. Where this blue car, we need to overtake this. Our inputs currently is that we know our current states and we know where exactly we want to go. So after this, to get to that state is actually relatively simple. What we need here is steering, brake, and acceleration for getting from here all the way to here. And on each point of our journey as we are traveling, we need to constantly calculate the deviation between the current location and the target of where we need to go. And that's basically it for control. We have the inputs, we know what output we need, and the car just steers, brakes, and accelerates till it gets to where it needs to be. So now let me talk about rule-based systems. What are rule-based systems? They're a system that apply human-made rules to store, sort, and manipulate data. So essentially what this is saying is that the logic is human-made. We write the logic for rule-based systems. And an application of this would be speed limit, because that is something that is easily quantifiable. Let's say the speed limit is a certain number. We can write logic saying, oh, if the car exceeds this speed limit, do something. That logic is relatively easy to define. We don't need any artificial intelligence. We can explicitly program that logic. So due to its simplicity, it offers some advantages. It's very easy to manage and especially debug. If we have a problem, we can easily identify where in the logic we made a mistake and fix that bug with relative ease. There is no artificial intelligence. There is no neural networks used here. So it offers more certainty because we are the ones writing the logic. The output is more clear. And it's especially good for the control portion of autonomous driving. The control portion is the car just accelerating, braking, steering. All the AI work is done. So in order to navigate this control portion, rule-based systems are actually very, very important, very nice to use. But there are quite a few problems with this as well. The biggest problem is it can only take you to level 2 automation. That's the peak from what experts have said with the rule-based systems. And this is primarily because when it comes to driving environments and the different scenarios a car can face, we cannot hard code, we cannot write logic for every single scenario by ourselves. We do need some help for that. Furthermore, it's difficult to extend because if you think about it, writing one piece of logic with the speed limit, for example, is quite simple. Writing 2 pieces of logic, also quite simple. But writing and maintaining millions and millions of pieces of logic, it becomes that much more tedious and difficult to do. And finally, rule-based systems relies on the driving environment and the rules in it to be perfect. And that is hardly the case in the real world because as we drive, there's always going to be anomalies here and exceptions here. And there's going to be millions of such exceptions. So to write logic for each one is really, it's not feasible. It's very far-fetched. So there comes machine learning. It is an application of AI that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. And explicit programming is the keyword here. We're essentially not doing that. We're allowing the model to learn from the data that we pass in. That is very different from writing the logic ourselves. So some of the advantages is that it can take us up to level 5 automation. It's very easy to extend over situations that can be vast because in order to improve our model, we pass in more data and it learns from it. There is no need to write write out all the situations ourselves. And therefore, that makes it more suited for the driving environment as we see it. There are, of course, some problems. It's not all rainbows and butterflies. It's very, very difficult to debug because there is no linear approach to debug. Let's say we have 1,000 feature vectors. We cannot just say, oh, the bug is at layer number 512 because we don't know what layer number 512 even is. As the network gets deeper and deeper, it's that much more difficult to fix. Furthermore, although we can determine the number of layers, more layers or more data isn't always better. There can always be stagnation where we reach a point where adding more layers actually decreases the performance of our vehicle. That is called overfeeding, and you could definitely look into that after the presentation. So essentially, due to this, it offers far less certainty, which is a huge problem when you're talking about autonomous vehicles. So now I'll talk about something called reinforcement learning. It's, again, another way of training models. And it basically relies on something called the maximizing rewards principle. So Essentially, we're given a problem here, and we give our model a few options. And the model can try these options out to its will, however it wants. But every time it makes an action that is incrementally successful, we increase the reward for that action. So the next time the model is faced with a similar problem, it will take that same action. So let's say we're making a right turn, for example. If the car goes to the right lane, we would increase reward. If the car actually turns and succeeds making the turn, we maximize the reward at that point, so that the model knows that that is the approach to take in order to maximize reward. So I'll actually give you a demonstration of this, of several cars on a racetrack. The demonstration uses neat.python, and the code credits go to Neural 9 and Cheesy AI. The configuration of the maps is done by me, and I will show you in this YouTube video. This is me essentially just loading up the software. And around here, we will see anytime now, cars appear on the screen. Voila. Here are the cars, and they're trying to complete a lap around the track. But as you can see, a lot of them are dying right now. But each car is getting incrementally further than it got before. And that is the beauty of reinforcement learning. And finally, at generation 5, we have reached one car that succeeded doing the lap. As we can see this car in front, it's successfully doing the lap. You can also notice that the 5 lasers coming out of the car, they actually represent the sensors. So in this case, they're keeping track of the lane width and the things in front of the car. So now we are at generation 6, and we have successfully have 2 cars crossing the lap. As you can see here, some of the cars are actually faster than the others. This is because each car is a different model. It's independent of the others. And the options we actually gave it in the beginning are go left, go right, go forward fast, and go forward slow. So when the car knows that the fastest lap time is fastest lap is the maximum reward, it will always go faster. So this one, for example, the car that is currently moving, it's moving so much faster because that is the solution with the maximum reward. So essentially, we're at generation 8 now, and we have 3 cars alive, which is much better than earlier where we only had 1 car surviving. And in the beginning where we had no car surviving, here we have 5 cars making the lap. So essentially, that's a really cool model. I find it really amazing how the car actually learns from its own doings and can actually solve a problem with this. So that's a cool demonstration. I will now move on to the next slide. So in conclusion, which approach, you ask, is better? Is rule-based better? Is machine learning better? And the answer is no approach is perfect. It's highly dependent on the environment we're considering. If we have something like control, where we don't need to involve all this AI and all the uncertainties it brings, we can use rule-based systems. But in order to get to that phase, for computer vision, for example, AI is absolutely necessary. But one thing we can actually conclude from this is that to make the transition to higher levels of automation, especially level 4, level 5, if you want to push those levels, we do need some machine learning. And that is all for me. Thank you for listening. If you want to learn more about this topic, you can go to Udacity's Intro to Self-Driving course. I actually learned a lot from this, and I got a lot of images from this as well. Here's my email and my LinkedIn. Thank you guys. That's all from me.